Okay, grade 10, here we are with lesson number 6, graphing reaction rates. So here's your tell for today. You notice you have space for how we graph reaction rates. You're going to draw one of the graphs here for that. Oops. And then we have calculated reaction rate just for the formula for that. And here, average instantaneous, you're going to be doing some notes on it with a graph to draw. And then you're going to be doing your own answer some questions. So something you can answer here, and there's one graph you have to make. If you can use the graph app we used before in physics, you should use that one because you have to draw tangents. If you cannot use that app on your computer, then you can use just do it by hand. Okay? So your template, pause your video and draw the template. Okay, so let's talk about how we graph reaction rate. The graph you need to draw here is this one, where it's showing the classic curve of reactant decreasing and product increasing. I recommend you do a little clearer than this and actually use a different color line for each one, just to make it very clear in your notes. Okay, so when you're graphing a reaction, there's a couple of rules you have to follow. First of all, you always put time on the x-axis. And pretty much any time you're graphing for any field of science where you have time as a variable, time is going to go on the x-axis. And then whatever metric, whatever measurement you're using to measure the reaction rate, you're going to put it on the y-axis. So in this case, it's concentration in moles per liter. Make sure you really clearly label the units of time and your reaction progress tool on your graph. So here I have time in seconds, and I have concentration in moles per liter. I'm seeing a lot in this class when you guys do graphing for labs and things, you're not including the units and you're not including the labels. And without a unit and labels, the graph is useless, which is really unfortunate because you put a lot of work into making that graph, and then just by not doing that last little bit, all of a sudden it's no longer a useful tool for us, okay? So make sure you add the labels really clearly to every graph you do. So what are some of the different ways we can indicate reaction rate? A little bit last class, last lesson, talking about the various experimental designs for measuring reaction rate. Well, here's some of them. Remember delta, the little triangle means change in, it's the Greek letter delta, so change in concentration in moles per liter or molarity if it's a solution. You can do change in volume of a gas in milliliters or in centimeters cubed. You can do a change in mass, measured in grams. You could do a change in pressure, measured in kilopascals, any of those things. So here we have volume of gas, here we have mass system, something that you're using to show reaction rate. Could we ever use temperature, change in temperature? So we could definitely use temperature if we have a reaction that's really strongly endothermic or really strongly exothermic, because that means that reaction has enough of a temperature change that it's going to be showing the rate of the reaction. When the temperature stops changing, the reaction is over. So you can use delta T, temperature change, as a way to show reaction rate, but only if it's really strongly exothermic or really strongly endothermic. Just be careful with that one. Okay, so when you look at a reaction rate graph, what do you notice about the shape of it? Well, hopefully you're noticing a couple things. You're noticing here that the reactants starts high and gets lower gradually until it gets to zero. The product starts low and gets high. You should be noticing that we have this initial kind of sharper slope for both, a sharp increase, sharp decrease. You should also be noticing that we have a plateau. It's going to kind of end at one point. They both reach a plateau. What does that mean when it reaches a plateau, when the graph stops changing? Well, it tells us that whatever reactants were there have become products. There's not enough reactants left to make any more products, or there are so few that the chance of a collision happening between them to cause them to produce a product is so little it's unlikely that cause a reaction. But with the slope, how's the slope changing? Well, you should always notice that for almost every reaction, we have this really steep initial slope starting at zero, really steep initial slope for products, getting steep and slowly getting less steep as time goes on, and the exact opposite for reactants, starting really high and decreasing rapidly and then decreasing more slowly over time. The slope gets less steep, less big as time goes on. So we look here at this exact moment in time, that particular point, the slope is 1.06 times the negative 2 molar per second. So that's how many moles of concentration is decreasing of the reactant. So in this graph, we're only showing reactant. We're not showing product as well. Okay, so the slope changing shows you the reactant rate. The slope of this graph is the reaction rate. How many, whatever you're measuring, grams, moles per liter, degrees Celsius, volume in centimeters cubed, pressure of gas, how much of that is decreasing per second. So most graphs are like this one. You'll notice they only show either the product or the reactant. Why do you think that's the case? Well, we think about when we did our experimental design last lesson, it's really hard to measure both reactants and products. And to know a reaction rate, you just need to know one of them. Because whatever is, if the product is decreasing, reactant must be increasing. If reactant is is decreasing, then product must be increasing. Whatever's happening to one, the opposite is happening to the other. So you only need to graph one, and it's really challenging to measure multiple things in a reaction. Usually pick whatever part of the reaction is easiest to measure. Last class, I talked about the ability to measure gases being produced as an easy way to measure reaction rate. So the slope, so I'm saying this again to reinforce, it's a really important concept. The slope of this graph is what? It's the reaction rate, right? It's the change in reactant concentration, and are we measuring it? Concentration, mass, temperature, whatever, over time. And that's going to show you the rate of the reaction. Okay, so here's the form for calculating reaction rate. You should draw this, please, into your notes. Either one is fine. And so when chemists are comparing reaction rates of different chemical reactions, there's two things they can use. They can use the initial reaction rate, because that's the fastest reaction rate, the initial kind of starting point of the reaction. Here we have pretty quick initial slope, and then it really slows down after that. Or they can use the mean reaction rate. So the mean reaction rate can be calculated this way. So we have the quantity of the reactant that's been used up over time, or you can do quantity of product that's been formed over time. Just depends on which one you're measuring, which one you have data on. Either one is fine. But often the value of initial reaction rate and mean reaction rate can be very different from each other. Why do you think that's the case? Well, most chemical reactions are very fast at the beginning. When there's lots of reactants are plentiful, lots of collisions can happen. We're going to have a lot of products being formed. But as time goes on, it really decreases. Whereas the mean is the average of all the instantaneous reaction rates. So in this graph here, every dot is a reaction rate at that moment in time. It's an instantaneous reaction rate. Whereas the line would be the average. These are quite different, right? In this case, just plotted the first point and last point. But the mean would be the average of all these points put together. So what that means is the mean reaction rate is a lot lower than the initial rate, but it's much higher than the final rate. Right, so the exact midpoint of the reaction is the point where the mean should equal the reaction. Now this graph here, this line isn't actually the mean. This line is just showing, if we just plot the initial and final, how inaccurate that is. So be careful with plotting the mean versus initial and final. It's not the same thing as just plotting any 2 points in a graph, joining them, and therefore you have an accurate representation of the slope of that line. That does not work for this, so be careful. Okay, so here's some example problems. So here we have a reaction, we have calcium carbonate reacts to hydrochloric acid, so we looked at before, and 40 centimeters cubed of carbon dioxide was produced in 10 seconds. Calculate the mean rate of reaction during this time in centimeters cubed per second of carbon dioxide. So here's my formula. Rate of reaction is quantity of product over time. 40 centimeters cubed over 10 seconds gives me 4 centimeters cubed per second. Notice I have the formula, I have substitution, I have my answer with units. Here we have another example with magnesium reacting with sulfuric acid. 0.1 gram of magnesium used up in 20 seconds. So what's the time? The reactant was used up this time. It's that product measurement reactant. 0.1 grams of magnesium for 20 seconds, 0.005 grams per second. And here we have copper carbonate decomposing when it's been heated. So we have 0.024 moles of copper carbonate decomposed in 30 seconds, the mean rate in moles per second. So 0.004 0.024 moles over 30 seconds is 0.0008 moles per second. Now there's 3 of these examples, not because the calculus is complicated, but because the units are all different, right? Here I have volume of the gas, here I have mass, here I have concentration. So it's really, really important, even more than any other time, to make sure you have units for every single calculation, because the units for reaction rate can vary greatly based on how you're choosing to measure the progress of the reaction. So here are 3 practice questions for you to do, and this is part of the homework for this lesson. You're going to pause the video, do those problems now, and there'll be 3 more problems that are graphing problems to do after this. Okay, so pause the video, do these problems, make sure you write the formula, substitution, answer with units. Okay, last part of this lesson is talking about mean versus instantaneous reaction rates. So we're going to look at this reaction similar we looked at last class, where we have calcium carbonate plus hydrochloric acid gives calcium chloride, water, and carbon dioxide. And this is that graph of that reaction. It's the same, the green line is the same for both of them, it's the same one. And this is showing volume of carbon dioxide produced. Remember, we measure carbon dioxide for this reaction. It's the easiest way to measure reaction rate because this is dissolved in the water, it's hard to separate them. This is dissolved, this is a solid that once you mix it, it's hard to separate to see how the mass is reducing, so we use the gas. So this curved line, the reaction rate line, is simply connecting all of the instantaneous reaction rates. So if I was plotting this data, let's say I was collecting volume data with a vernier probe, a pressure sensor, or measuring volume, I would have these different data points at 15 seconds, 30 seconds, 40 seconds, just plot those points, and then I would connect them with a line, okay? Now, if I plotted the mean of all those points, it would just be a straight line, right? Something like that. So to determine the instantaneous reaction rate at one instant, at one moment only in that graph, how do I do it? You're given a graph with a curved line like this. How do you figure out the reaction rate at one particular moment? Well, hope you can see the picture here. They do it with tangents, good old tangents. So we've drawn a line here. This is at the point for 45 seconds. And drawn a tangent. The red line is the tangent off that line. And then measure the slope of the tangent, 50 over 45. So I'm going to get my change is 1.11 centimeters cubed per second. That's my rate at that time, okay? And then here, my second tangent point up here, here's my red tangent line, and again, I'm going to calculate the slope of that line, 0.53. So look how much is decreased. Here's a much higher reaction rate than over here. So you need to be able to do a tangent to be able to do this. Anytime we're measuring the slope of a curve, we're going to use a tangent. Okay, so here's some practice questions for you. So first one's about this graph. You have these different points to talk about and identify, A, B, and C. And then question number 5, you have this graph to use, P, Q, and R. A and B, make sure you're explaining your answers. Okay, guys, so just give me a letter, explain why, how you know that. So pause the video, answer these questions in your notebook, or if you're usually that's fine. And the last question here is a data set for hydrogen gas being formed when magnesium reacts with sulfuric acid. You need to calculate the rate, plot a graph, and I want you guys, if you have the ability, to use that app we downloaded for physics called Graph, because it lets you do tangents. If you don't have that app because your computer won't let you use it for whatever reason, then you're going to have to do it by hand. And we know graphing tangents by hand is a pain in the butt, and it's really inaccurate. So if you delete a graph, try and get it back. If you don't have it, then try and find some other way to do tangents or do it by hand. Okay, it's an important skill to have for next year. And then calculate the rate at 20 seconds and the rate at 40 seconds with a tangent. And then E is the last part, you're going to draw a word equation, so writing the reactants and with their full names and words, as well as a balanced equation using the chemical symbols and balancing it for this reaction. Okay, so that's the end of this lesson. You need to include all the notes for today's lesson in your upload, as well as all 6 practice questions. And that should include your graph. So you're welcome to, if you do it on Graph, the app Graph, you're welcome to use a screenshot and put that in your notes to upload and show you did the work. If you did it by hand, just upload a picture of it. Double check also your big ideas. The first 3 are done. We're going to finish the next one next class. And then we'll be using that to for your final exam. Your final exam is based on the big ideas. So you've been doing a really thorough big ideas this whole unit, this whole year, you're in really good shape for that final. If you've been doing really lazy ones, you're going to have to go back and fix them to be able to do well in the final exam. Okay, guys, I hope this was helpful for you. If you have any questions, please ask at our Zoom meeting. Send me an email. Happy to help. Take care.